In this video we will talk about the periodic trend with regards to effective nuclear charge. So effective nuclear charge is essentially abbreviated Z sub F, so for effective nuclear charge. And to better explain it, we will draw a very crude model of an atom. This is like how Bohr envisioned the hydrogen atom. So a typical atom will have the protons and neutrons housed in a nucleus, and then sort of orbiting around it are these different electrons clouds. And electrons can be part wave, part particle. And the electrons, as you try to visualize this, the electrons are going to be housed in p orbitals, d orbitals, and s orbitals. But in this pictorial diagram, we'll see that we have electrons that are sort of nearby the nucleus that houses the protons and neutrons. Protons are positively charged, neutrons are neutral charge. And then we have electrons that are sort of outside. So effective nuclear charge basically is stating that the protons here that's positively charged are going to really attract the electrons, right? Because positive will attract negative. The positively charged protons, the atomic number of the element, will attract the negatively charged electrons. But really the attraction is more towards the core electrons. Okay, the core electrons here. The outer electrons really do not feel the full brunt, the full effect, and the full attractive qualities of the protons housed in the nucleus simply because they're outer, and also because most of the attraction is being felt by these core electrons. So the effective nuclear charge basically is stating that these outer electrons, if I were to highlight the outer electrons here, in orange, in the orange boxes, the outer electrons, these are the ones that participate in ionic bonding. These are the ones that participate in covalent bonding. These outer electrons do not feel the full force and full brunt of the protons. So the valence electrons have a little bit more, they're a little bit more loose because they're not more tightly held. The protons are really tightly attracted to the negatively charged of the inner electrons, also known as the core electrons. So this lessening of attractive force is technically known as the effective nuclear charge. Another way you want to think about this is that pretend I'm in the center of the room lecturing to you guys, and I'm in my class lecturing, and I yell. So who's going to hear most of my yelling of my lecture? Okay, is it going to be the students that sit in the front of the class or the students that are going to sit in the back row? Well, obviously students sitting in the front, first row, second row, are going to really experience my yelling, my screaming, my lecturing, my whatever. Those in the back row are kind of shielded, so this is also known as shielding. So let's look at the trend of the effective nuclear charge. The effective nuclear charge actually increases from left to right in the periodic table. So here we have an increase, and then the effective nuclear charge, or shielding, also increases down a group of the periodic table. So this is a situation where the shielding increases left to right across a period, and shielding, also known as effective nuclear charge, increases down a group in the periodic table.